Okay, so let's continue with some extra considerations, very general, about ferroelectrics. And today we are going to talk actually for the first time about the one defining feature of ferroic phenomena, right? Which is that this order parameter that we have been discussing should be switchable. It should be possible to move between the positive polarization and negative polarization state, likewise with magnetization or with the strain, by application of the conjugate field. All right, so we are going to be talking about ferroelectric polarization switching. All right, so before we do some mathematics with using our Landau potential for that, let me just briefly introduce how switching proceeds experimentally, right? So when we talk about switching, we are typically expecting to see some sort of hysteresis loop of this form. So polarization versus electric field would do something like this. But what are these states in reality, right? I mean, so for example, if we think about, let's say, states A, B, and C, and of course here we'll have D. Well, state A is our state with zero applied electric field, where we have a spontaneous polarization. So spontaneous means that it doesn't need an electric field to exist. So we can think about it as our sample showing this positive electric dipole in every cell. So if we look at any cell in the system, if you remember this little model crystal we introduced in the first lecture, well, we'll have the situation where the atoms are everywhere. These central cations, they have moved up. So locally we have a positive dipole, okay? And that happens everywhere, homogeneously, let's say, or ideally homogeneously. This would be a state A. Now, if we apply a negative electric field, therefore a field that goes against that polarization, as you can see from the typical hysteresis curve, the polarization is going to reduce in magnitude. What does that entail in reality? Well, typically you start seeing the nucleation of domains with the opposite polarization, right? So you still have pretty much overall a positive polarization, but you start seeing regions where the negative, where the polarization points against the initial one, right? And follows the field. So here I am applying a negative electric field. Okay. These regions, so you nucleate this kind of transformed domains. They tend to have the shape that I have drawn there. That's not arbitrary. That's because as much as possible, the system typically avoids forming charged domain walls, but that's not very, very important here. It's only important to remember that you have intermediate states where the polarization is not homogeneous at all. Right? If you see this, you could imagine that maybe the polarization becomes smaller everywhere in the sample in a homogeneous manner, right? To go from A to B. But that's not what happens at all. Typically, what happens is that you have regions of positive polarization with a magnitude that still is very much the one that you have initially, and regions where the polarization is negative. Okay? So state number C would simply be, we typically call that the coercive field, the field corresponding to state number C, but that is nothing else than a state where the positive and negative polarized regions more or less are compensating each other. Okay? And finally, state D, well, as you can imagine, if I keep increasing the negative field, eventually the negatively polarized regions win over the positively polarized regions, and I can go finally to a state where I maximize my negative polarization, which means that the whole system is homogeneously polarized in that way. Okay? So this is what happens essentially in real ferroelectrics. What is interesting is that here we are describing the state of the system by a single number, the polarization. So when we say P equal to 0, actually when we introduced our Landau theory at the very beginning, and we were talking about the P equal to 0 state, we were imagining a state in a crystal where all the atoms, or wherever you look in the system, in the crystal, you have that configuration, right? We were saying that this is P equal to 0. And we were saying that something like this is P positive. And that's fine, of course, that is a state with 0 polarization. In reality, though, when we go through a state with polarization equal to 0 in a hysteresis loop, we are typically going through a situation like this. What is important to realize here, what I would like to emphasize, is that when you do something like a phenomenological Landau theory, you may not know much about the details of what you call the state with P equal to 0. Okay? In a sense, and actually your theory can describe that or that, and what you are describing is probably context dependent. So if we are discussing something like switching, what we describe as P equal to 0 is something like this, effectively. Okay, we can fit to experimental information, or we can fit to atomistic information maybe, but what we call P equal to 0, if we simply monitor the polarization, may actually be something like this, and not something like that. Okay? So our theory is agnostic to that. It doesn't care. The only important point is that if your theory is detailed enough to study the phenomena of interest, then you are fine. In some cases, of course, you may want to go into properties that force you to distinguish whether by P equal to 0 you mean this or this. Okay? So not all the properties, actually almost no property at all, is the same for this state as it is for that state. And if you want to disambiguate, so to speak, you may need a more detailed theory that describes the polar state not with a single number, the polarization, but maybe with a field, with the polarization field. Okay? But for the time being, we are going to work with the simplest theory, describing the polar state by simply by one number, the polarization. Okay? And keeping in mind that when we talk about switching, the switching doesn't happen like up, 0, and then down. It happens like up, 0, and then down. Okay? Although that will not be explicit in our consideration. All right? Okay. So let me remove this one. And now we are going to see how our very simple Landau model allows us actually to describe ferroelectric switching. All right. So if you remember, we had introduced like the simplest possible potential that was able to describe a continuous phase transition. It was a fourth order Landau potential, right? So we are going to use this one, this very simplest of potentials, to also try to see if we can describe switching. Okay, so just as a reminder, we had something like Fp of t, which was something like this, alpha prime t minus t0 or tc. In the case of a continuous phase transition, this parameter is actually the Curie temperature already. P to the fourth. And we know that the electric field couples to the polarization in that very simple way in an energy that is expressed in terms of, in units of energy per unit volume. So this is actually energy density. All right, so here alpha prime, beta, and tc are all positive numbers. Otherwise, it doesn't make sense. And we know that this allows us to describe a continuous phase transition. All right. Now, before we start doing detailed mathematics, let's try to do some things graphically. So if I plot this f function as a function, f as a function of polarization, and if I plot this for a temperature below Tc, an electric field equal to 0, we have this famous double well potential, right? That's simple enough. Okay. Actually, for convenience, let me call this guy, when the electric field is 0, let me call it F0. It will be convenient to make a distinction. So F0 is simply the first part of F, so all this part. Let me call this thing F0. Okay. Now imagine I turn on a positive electric field. Let me draw that one in green. Imagine I put that extra term. So for the moment, actually, in every consideration that we had done, we were dealing with the electric field at most in the perturbative way. We were considering derivatives with respect to the field, but we have never actually dealt with a finite electric field. And this is going to be the change here. Now we are going to deal essentially with an electric field-induced phase transition. It's a particular kind of phase transition because we are going to jump from polarization up to polarization down. So this is a transition between two states that are equivalent, actually. So here there is no symmetry breaking. Since the phase is the same, it's funny to call it phase transition, but certainly it's a field-driven transformation. Okay. So we need to consider finite values of electric field. Now, the electric field with the polarization just adds a linear term like that, right? If the electric field is positive, that means that positive polarizations will have an energy that is lower than negative polarization, right? And this dependence is odd with the field. Well, it's simply a line, so let me just draw it like this. Oops, it should cross through 0. So the electric field just adds to the free energy a dependence like this. This is minus P. And the total potential under an electric field is just the addition of these two potentials, right? So we have to F0 plus. So if I plot it in blue, F is simply F0 plus that. What do I get? Well, I get something that here at 0 is the same, but eventually this minimum is very much down. So this starts linearly there, then it goes down. Maybe the minimum goes there. And we know that this minimum is going to go up because here I have to add to this energy the green contribution, right? So that minimum is going to go to something like this. So let me emphasize the blue one. So the total free energy under field starts looking like that. So then the basic thing that an electric field does is quite obvious, and it is also obvious that this simple theory may allow us to describe phase transitions, right? Not phase transition, sorry, switching. Why? Because if I start here at 0 field, imagine I start in a negative polarization state. When I put the field, essentially what I'm going to do is to penalize the energy of this state, so the energy goes up, and eventually this state will come all the way here. Not this state, the system. The system will change the state from a negatively polarized one to a positively polarized one. Okay? So in a very simple graphical way, this is what ferroelectric switching is, and obviously is captured by our Landau potential. All that we need is two minima that are equivalent in the absence of field, and that can be, whose relative stability can be played with when we apply an electric. It's as simple as that. Also, you will see it mathematically in a moment, but if the field is large enough, positively large enough, this minimum, we can make it disappear altogether. All right? Okay, so this is the basic thing that our theory has to capture. It is here, so it has to capture. Now, let's try to do this mathematically. And this mathematical exercise is actually quite interesting because it forces us to deal with a problem that, generally speaking, we cannot solve analytically. All right. So let me go to black. we start with that Landau potential, and as we know very well, to study the equilibrium states of any of these free energies, we have to look for the situation, for the values of the polarization that make this that define minima of this potential for given values of temperature and electric field, right? So essentially, we need to make the first derivative of f with respect to p at equilibrium has to be 0, exactly as before, and we have done this one already. This is alpha prime t minus tcp plus beta p to the third equal to the electric field. We call this thing equation of state, and we have to find its minima. The difficulty now is that we want to do that for finite values of the electric field. Okay? So you remember when the electric field was 0, the first thing what we did was to take common factor of the polarization. That was one solution, and then we were left with the second order equation, polynomial, which is trivial to solve. But when we have a situation like this is less trivial, certainly. And to continue analytically for arbitrary values of the electric field, potentially large, would be painful. Let's call it that. Okay. So what can we do? So one thing that we can do here, and actually it goes back to understanding what the equation of state is to realize the following. This equation tells us the equilibrium values of the polarization for any choice of electric field and temperature. Okay? That's fair enough. It also tells us that if we wanted to have, so in that scenario, when we think in this way, we are thinking that the electric field and the temperature are the inputs of our problem, and the equation tells us the polarization. Right? However, we can also think in the following way. Imagine I am at a certain temperature, and I would like to compute the electric field that I need to apply for the polarization to have a certain value of equilibrium. This equation also tells us that. So we can understand this equation as a function of polarization and temperature, as the functional form or the expression for the electric field as a function of polarization and temperature. Okay? And what is this electric field? This is the electric field I have to apply to get such a value of the polarization. For example, let me draw it like this. Let me go back to plotting here F0 at a given temperature, always below Tc. And this electric field is the derivative of F with respect to F0 with respect to P. Okay? Which let me plot here. Let me plot here the electric field, which is the derivative, the first derivative of this curve with respect to the polarization, right? So if I want to stabilize a polarization of that value, what this equation is telling me essentially is that I have to apply an electric field that corresponds to the derivative at that point. That makes good sense. If I am here with the polarization in the absence of field, the polarization, the system will essentially feel a force that is simply the derivative of the energy with respect to the polarization, bringing it to a minimum. Okay? So the electric field I need to apply to compensate for that force, so that this point becomes a minimum itself, is exactly the slope, but changing the sign. Okay? That's exactly what we are doing, or what this equation is telling us. And so it makes good sense to plot here that electric field as a function of polarization. Okay, so the electric field, as I was saying, is simply the derivative of F0 with respect to P. And to plot this, what is a good way to plot this? We can, for example, label the important points, the special points here, A, B, C. So those are points where the first derivative of this function with respect to P is 0. So Okay, so at those points, A, B, and C, the electric field has to be 0. Makes good sense. To have an equilibrium polarization at the minimum, I don't need to apply any field, right? That's what this is telling us. And then what else do we have? Well, we took here, obviously, this slope is negative. So over here, I have to go towards negative. It makes also sense. I need to apply a negative field to move from here to polarization values over there. Okay. This function, by the way, is odd with respect to changes of sign in polarization. So if this branch goes negative over here, I already know that the corresponding branch goes positive over there. And what happens in the middle? Well, something quite simple, right? In the middle, if I think about the derivative of this function, it interpolates by doing something like that. Okay, so over here in this range, I have a positive derivative. Over here, I have a negative slope. And obviously, there are points of maximum slope which correspond to a couple of hidden inflection points there. Okay, so from the function of the free energy as a function of polarization at zero field, if we take the derivative, we get the values of the field I need to apply to stabilize different values of the polarization. So without solving this at all, we are getting some important information simply graphically and trying to understand what things mean. All right, but that's not the whole story, because this curve might invite to think that if I apply a zero field, for example, here, or if I apply a field like this, if I am here, I could obtain values of polarization. I could stabilize my system with a polarization of equal to 0 or this kind of polarization at the temperature in which it presents this kind of free energy. Okay, and that's not true. This condition is an equilibrium condition, but we have to introduce an additional consideration to identify the situations that give us a stable equilibrium. Okay, so if I apply zero field, this value, this state, corresponds to equilibrium, but is unstable equilibrium. Okay, and so if we think about the condition for stability, well, we simply have to take the second derivative of f with respect to p2 times. This happens to be the same as the second derivative of f0 with respect to p2 times, by the way, because this term goes away. We were calling this stiffness, and we know the expression for this, right? It's alpha prime t minus tc. But let me emphasize this here. Oof, 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 oof. This second derivative is also the second derivative of this P0 energy that we are using with respect to P2 times. And this, of course, analytically, we know what it is. But graphically, it's even simpler. So from F0, we went to the electric field by taking one derivative. And if we take another derivative, so the first derivative with respect to P of this curve, we are going to go to the stiffness. Okay, so let's do that. It would have been nice to do it below, but it doesn't fit, doesn't matter very much. So let's again see if there are some special points here, right? I mean, let me do it with a different color. So we are taking derivatives. So of course, the points of zero derivative are a good guide to draw things. So we had A, B, C. Now we are going to define D and E. Those 2 points have zero derivative. So if I put here kappa, this is my kappa. We know that these points, well, let me draw simply here A, this is B, and here I'm drawing now E and C. Here I have 2 special points, D and E, where this function has to be 0. Okay. These points A, B, and C, I draw them, but actually they are not so important to analyze this. And then what do we know? So to the left of this point D, the slope is positive. To the right of this point E, the slope is positive. Okay, so I have something like this. And in between, in the region in between D and E, the slope of this curve is negative, right? So I have something. We could do this in more detail, but of course, you see from the analytical expression, we essentially have a parabola, which is what we get. This parabola has a negative value at p equal to 0 for temperatures below Tc. So here we have negative value, and then it goes up because the curvature is positive, right? But what is interesting here, of course, is that for us to have a stable equilibrium, we need to be in situations where the stiffness is positive. So it means that in this region here and this region here, so for polarizations smaller than this one and bigger than this one, those are states that are good, are physically relevant. And the region in between corresponds to a state that are unstable equilibrium states. Okay? So if we drew them with red here, we are essentially saying that we have a region there in between where the system is not stable. We cannot access those states, but by simply applying an electric field, because they are not stable equilibrium states. Okay, but outside that red region, yes, we can access all those other states by applying an electric. Okay, so that pretty much completes the analysis. We haven't solved anything explicitly mathematically, but we have pretty much figured out how our system responds to an electric field of arbitrary value. You see here, I have electric fields of arbitrary value, and I have all the collection of polarizations I can have for those fields. This sounds very good. Now, of course, this must be related to the polarization switching, right? I mean, we have collections of states that happen for fields of arbitrary value. And so how does this relate to polarization switching? Well, to see the connection, we are going to do also something pictorial and very simple, because actually in one of our figures, we already have the hysteresis loop as provided by this theory, right? So let me make some room. So when we plot a hysteresis loop, we plot polarization versus electric field, and somehow a hysteresis loop is also a collection of points in this plane where the system can be in equilibrium, right? And here we have a slightly different representation. We have electric field versus polarization. We already discussed how to interpret this. This is how much field I need to apply to stabilize certain polarization. But this already gives us a collection of states that correspond to equilibrium states of the system. Okay? So if we try to simply redraw these, but swapping the axes, what do we get? Right? I mean, essentially, these two things must be the same thing. Okay, so let's think about that. So this point A, for example, is the one that we had for negative polarization at zero field, right? So this point A must be here. This point C was the one that we had at zero field for positive polarization. So it could be somewhere like here. Points A and C, okay? And then there is also interesting, these two interesting points, D and E, they correspond to the limits of our stable states, right? I mean, over here we can go, but beyond D, things become unstable, likewise, right? So point D is in the quadrant with positive electric field and negative polarization, right? So point D, therefore, is in the quadrant with positive electric field and negative polarization, so it must be somewhere here. And there has to be a symmetry-related point E, which is in the quadrant of positive polarization and negative electric field. So positive polarization and negative electric field. So this must be somewhere here. Point E. So maybe I have done this very slowly and carefully, but you can already see that I have a curve of possible states starting at D, going through A, and then simply going to very large negative polarizations for very large negative fields, right? So this is something like this. We go towards negative polarization in fields, and over here we have a similar situation where eventually we go towards large positive polarizations as large positive. So now, what's going to happen in reality according to this theory? If I start with my system there, let's imagine, no? At time 0, I start with my system in a positively polarized state. At 0, apply the electric field. And now I apply a negative electric field. What I'm going to do, of course, is to reduce the value of that positive polarization until I reach a point where the state with positive polarization is not a minimum any longer. That's literally what this stiffness going to 0 and becoming negative is telling us. Or that's what we were doing before. I'm saying I start here, I put a negative electric field, and what I'm going to do is to go to a very deformed situation where I have a very deep minimum over here, and this guy stops being a minimum. Okay, that happens exactly at point E. So at point E, if I get there with a field and I apply a field even a little bit more negative, what the system is going to do, of course, is to fall to the only minimum available for that value of the field. And that is a minimum with negative polarization. Which in this pictorial view would correspond to the system rolling down to that other minimum. Okay? So here we are reaching the limit of stability of the state with positive polarization. And once we go beyond that limit, obviously the system has to do something. It falls to the minimum nearby. It's very similar to what we saw with temperature for a first order phase transition. Here is not exactly a phase transition because these two phases are the same phase. They are symmetry related. But certainly is a discontinuous transformation. And this discontinuous transformation gives us hysteresis because if I do this, so I am 1, 2, 3, and now I apply a positive field, what I'm going to do? Essentially, I'm going to favor states with positive polarization, and this minimum with negative polarization eventually will go up and stop. It will stop being a minimum. So I can go this way, and I can go back this way, and eventually induce the related phase transition. Okay? So you can see our theory was hiding also the answer to hysteretic behavior under field switching. Of course, it gives us a very specific prediction for the electric field we need to apply to destabilize the minima. Okay? This is what we would call coercive field. All right. And essentially this is it. Then what is cool also is that, for example, if we think about this coercive field, you see that essentially in the hysteresis loop like this, there are several outstanding features, right? I mean, there is essentially the spontaneous polarization that we have at 0 field. And then there is the field that I need to apply to force the phase transition. No? In practice, the transition may happen before this theoretical coercive field, as we know, because there is thermal activation, because things may happen a bit earlier. But we know that the transition cannot, I mean, if we are at the coercive field, something has to happen, because we lose the minima. One thing that one can think of, I mean, we haven't done any math, but the coercive field in particular is something that is very simple to calculate, right? Because the coercive field essentially corresponds to these points where the curvature, I mean, the derivative of the electric field with respect to polarization is 0, meaning that the stiffness coefficient is 0. The stiffness needs to be positive for stability, so when it becomes 0, we lose the stability, right? So essentially, the coercive fields are something that, let me, for completeness, I'll just indicate how we could compute them from the theory. So we had the equation of a state. We have the stiffness, second derivative of f with respect to p 2 times, which coincides with the second derivative of what I have called f0 with respect to p 2 times. It's a very simple thing, alpha prime t minus tc 3 times beta p cube. And so the condition to be at the coercive field is that when the field is the coercive field, this kappa is equal to 0. So of course, you could say, well, okay, I can make this one equal to 0. Great. But there is no electric field in this expression. That certainly seems to be a difficulty. Oh, sorry, there is a square here. But there is a polarization. So if we make this equal to 0, we will be solving for the value of the polarization at the coercive field, okay? Which corresponds to this one over here and this one over there. It is so simple that we can do it. So the value of the polarization at the coercive field is alpha prime tc minus t over 3 beta, square root of this, right? With a plus and a minus. And if we want the coercive field, what we have to do is to take this coercive polarization and plug it here. The coercive field will be given by that expression that we have there when P equals to this, right? So again, very quickly, can we do this one quickly? Let's see. Let me take the positive value of the polarization, which will correspond to this coercive field, to this one here. We expect that for a positive coercive polarization, we should obtain a negative coercive field. So let's do that one. What do I get? So I get alpha prime tc minus t 1/2, so 3/2, the minus in front, square root of 3 beta. Did I do that right? No. Yes, that's correct, I think. And here I have this to the cube. I'm going to have a plus. So I have beta, 3 beta, 3/2, and I have here alpha prime tc minus t 3/2. It is looking reasonably okay. Okay. So here I have something like alpha prime tc minus t 3/2, and then I have over a square root of beta, and then I have minus 1 square root of 3 plus 1 over 3 square root of 3. If I haven't made any mistake, this should be, so 3 go up, so we have a 2, so something like minus 2 times 3 square root of 3 beta alpha prime tc minus t. So please check for mistakes, but essentially the coercive field. There are some nice things here. My God, looks like it's bleeding. It looks like the whiteboard is bleeding blue blood. One thing is that for the positive, we took the positive PC and we are getting a negative coercive field. That's reassuring because that's how it should be. What else do we have? We have here something that is not trivial, of course, because this is this number below the root has to be positive. So this stuff can only happen for temperatures below Tc. That's good. We have to be in the ferroelectric phase to have a coercive field. So that doesn't bother us. And this expression is also telling us that when the temperature goes towards when we go towards the Curie point, the coercive field becomes smaller and smaller, which makes sense. If you have, what is the physical interpretation of that? Let me make room here. If you are very far away from the Curie point, you have very deep energy minima. But if you are very close to the Curie point, in this theory, you have very shallow energy minima. And it makes a lot of sense that to switch between these two states, you need a coercive field that is smaller and smaller. In the limit, when the minima are very close and very, very shallow, the coercive field tends to 0. Okay? That we see from there, and it makes sense. Okay, so with this, we conclude our discussion of ferroelectric switching, phenomenological, and then based also a bit more mathematical, but based on a very simple theory. And now, yes, now we know all the essentials of what ferroic order is, because all ferroics do this. They should be able to switch between symmetry equivalent states. Questions?